In this video, we're going to look at algebraically defined vectors and the dot product between two vectors. In our last video, we did look at vectors. We introduced them. We were looking at this geometric defined vector. So we were using them to find things like resultants and equilibrants, setting up images involving bearings. In this video, we're going to look at it a bit more abstractly. So let's first define a position vector, and that's a vector that has an initial point at the origin and a terminal point at some ordered pair AB. We use different notation for a position vector, illustrated here, where instead of using parentheses for that ordered pair, we're using instead of using those parentheses like an ordered pair, we're going to use those triangular brackets. Some textbooks and programs call this the component form of a vector. So we have a visual here showing a position vector, again, that initial sides at our origin 0, 0, and a terminal side at some ordered pair AB. The magnitude of the vector, which we did see in our previous video, is the length of the vector. And we can find the magnitude of the vector by manipulating the Pythagorean theorem. So the magnitude of the vector is equal to the square root of a squared plus b squared. We're also introducing new notation here for magnitude, where we've got absolute value bars around the name of that vector. We also have a direction angle of the vector. The direction angle theta is a positive angle starting at the positive x-axis, and we can find that directional angle by utilizing our tangent function. Tangent of theta is equal to b over a whenever a is not equal to 0. Find the magnitude and direction angle on the interval of 0 to 360 degrees for a vector 3, -2. So we're going to start by plotting this vector. 3, -2 is in our fourth quadrant, so I'm going to go ahead and set up my axes to emphasize the fourth quadrant. And I'm going to plot this endpoint just like I would plot any other ordered pair. So go along 3 on the x-axis, -2 on the y-axis, and that's the terminal point. And we can create that vector, that position vector, starting at the origin and going to that point 3, -2. Let's start by finding the magnitude of that vector. So the magnitude of our vector u is going to be equal to the square root of 3 squared plus b squared, or -2 squared. So the magnitude of u is the square root of 9 plus 4, or the square root of 13. Now to find that direction angle, remember the direction angle starts at that positive x-axis and is measured counterclockwise, just like we've measured angles in the past. So on our picture, we can see there's theta. But what we're going to use is this right triangle that we've created here in the fourth quadrant to determine our reference angle, theta prime. So we're going to do tangent, and I'm going to call this theta prime is equal to opposite over adjacent. So that's going to be -2 over -3. I'm sorry, -2 over +3. And we're going to use inverse tangent to solve for that theta prime. Now, if you recall those properties of our inverse trig functions, in particular inverse tangent, the output's always going to be an angle between -π/2, or -90 degrees, and π/2, +90 degrees. So we're going to get an output of theta prime to be -33.7 degrees, which is really just measuring that angle from the positive x-axis clockwise. So that angle theta prime is the same as 33.7 degrees. That negative just gives that direction. So then to find our direction angle, theta, we're going to take 360 degrees and subtract that 33.7 degrees. We find that our direction angle is 326.3 degrees. Write the vector in position vector form or that component form, given the magnitude of our vector is 198 and our direction angle theta is 128.5 degrees. So we need to find that ordered pair of that terminal point of our vector. That's how we're going to set up that vector form and component form. So let's begin by sketching an angle of 128.5 degrees. Starting at our positive x-axis, 128.5 degrees is going to take us into that second quadrant. And I'm not going to emphasize or worry too much about how far into that second quadrant. This is just going to give me this visual here. So this angle is 128.5 degrees. And we know the length of this vector is 198. That's our magnitude. So now we need to find our A and our B. And we know that A is going to end up being negative because we're in the second quadrant. That x coordinate is negative. So we've created this right triangle here. And if we find our interior angle of that right triangle, let's call it theta prime, we're going to use the definition, or we're going to use supplementary angles to figure that out. So theta prime is going to be 180 minus 128.5 degrees, or 51.5 degrees. So we know that this angle is 51.5 degrees. And now I can use the definition of sine to figure out the length of B. Sine of 51.5 degrees is equal to opposite over adjacent, so B over 198. B is equal to 198 times sine of 51.5 degrees. We get that B is 154.96. We aren't given any units here, so we'll just leave it off. Now, likewise, we can use cosine of 51.5 degrees to find the length of A. Cosine of 51.5 degrees is adjacent over hypotenuse, or A over 198. So A is equal to 198 times cosine of 51.5 degrees. And when we evaluate this, we're going to get a positive value because cosine of 51.5 degrees is going to be positive since we're looking at a reference angle. But because we are in the second quadrant, we know that A has to be negative. So this is going to be negative 123.26. So now we have our coordinates of that position vector, A and B. Our vector is going to be negative 123.26, 154.96. Write the exact vector in our component form, given the magnitude of our vector is 10 and our direction angle theta is 120 degrees. Now, again, emphasizing that when we see directions that include exact values, that means we should not be reaching for our calculators. We're going to be utilizing the unit circle here. So similarly, I'm going to set up I'm going to start graphing my vector with the given information. The direction angle is 120 degrees, which puts us again in that second quadrant, where this angle is 120 degrees, and the length is 10. Now, this does set up a right triangle in our second quadrant. And because of the supplementary angles, we know that this is actually a 30, 60, 90 triangle. Because our direction angle and this other angle are supplementary, that makes this lower angle 60 degrees and that top angle 30 degrees of that right triangle. Now, we know a lot about 30, 60, 90 triangles in the unit circle, but let's generalize those rules. So for our 30, 60, 90 triangle, let me draw that a little bit better. For our unit circle, we know that the radius is 1. We know that the x-coordinate's 1/2 and the y-coordinate is square root of 3/2. But if we generalize this for any radius, r, the side opposite our 30-degree angle is going to be 1/2 times r, or r divided by 2. And then the side opposite our 60-degree angle is the square root of 3/2 times that radius r. So we're going to use this extension of our 30, 60, 90 triangle to figure out the side lengths when we have a radius of 10. So if our radius is 10, or the length of our vector is 10, the side opposite the 30-degree angle is going to be half that. So this is going to be 5. And the side opposite our 60-degree angle is going to be the square root of 3/2 times that length of the hypotenuse 10, which will then simplify to 5 times the square root of 3. Now, since we're in the second quadrant, that first coordinate, that x-coordinate is going to be negative, so this is -5. And our y-coordinate, the second coordinate, is going to be +5 square root of 3. Let's look at some vector operations. Operations being addition, multiplication, subtraction. We're going to let a, b, c, d, and k all represent real numbers. If I want to add two vectors, all we're going to do is add their corresponding components. So vector AB plus vector CD is equal to vector A plus C, and then B plus D. If we want to take a vector and multiply it by a real number coefficient, we're just going to distribute that real number coefficient. And then subtracting two vectors works very similarly to addition. We're going to be combining like factors, but now we're going to be subtracting. So vector AB minus vector CD is equal to vector A minus C, B minus D. Another form that we can write a vector in is called the IJ form of a vector. So if we're given vector V is equal to AB, then the IJ form of that vector is given by V equals A times I plus B times J, where I represents the vector 1, 0, and J represents the vector 0, 1. So we're going to practice both vector operations and writing vectors in IJ form in this next example. perform each operation, and give the answer as a vector and in our IJ form. So really what we're saying is give the vector in component form and in IJ form. So we're given that vector u is -2, 1, and vector v is 4, 3. Our first example is vector u plus vector v. Oops. So that's going to be -2, 1 plus 4, 3. And we're just going to combine those corresponding components. So -2 plus 4 is +2, and 1 plus 3 is +4. That's that position vector form or that component form. And now to write it in IJ form, all we're going to do is write these as coefficients for I and j. So this is 2i plus 4j. -2 times vector u. So we've got -2 times that vector, -2, -1. -2, +1. And we're going to basically distribute. -2 times -2 is +4. -2 times 1 is -2. And there's the vector in position form, or that position vector or component form. And then to set it up in IJ form, this would be 4i minus 2j. Three times vector u minus 2 times vector v. So that's going to be 3 times vector -2, 1 minus 2 times vector 4, 3. Now we could think about, well, let's do the first vector. So we're going to distribute the 3 into vector u. So this becomes 3 times -2 is -6. 3 times 1 is 3. Now this next step, we can either distribute -2 and then it becomes an addition problem, or we can distribute 2 and keep it as a subtraction problem. I'm going to distribute the -2 and make this addition. -2 times 4 is -8. -2 times 3 is -6. And now we can add those corresponding components. -6 plus -8 is -14. And 3 plus -6 is -3. And our IJ form is -14i minus 3j. Now, if we look at these vector operations, we looked at adding vectors, we looked at multiplying a vector by a constant and subtracting vectors. The dot product is the result of multiplying two vectors. So that wasn't an operation that we'd seen above. The dot product is a real number. It's not a vector. If you've got two vectors, u and v, the dot product read u dot v. So be careful, that dot is not multiplication. Well, it is multiplication, but it's special multiplication between two vectors. So we want to make sure that we read it the correct way. Syntax is going to be very helpful in identifying whether that should be read as u dot v or u times v. But the dot product u dot v is equal to a times c plus b times d, where a and ab are the component form for vector u, and cd is the component form for vector v. Find each dot product. The dot product between vector 2, 3 and vector 4, -1. To find the dot product, we're going to do 2 times 4 plus 3 times -1. 2 times 4 is 8. 3 times -1 is -3. 8 minus 3 is 5. The dot product between those two vectors is 5. Vector 6, 4 dot vector -2, 3. So the dot product between those two vectors is going to be given by 6 times 2, 6 times -2, plus 4 times 3. 6 times -2 is -12. 4 times 3 is +12. -12 plus 12 is 0. So that dot product is 0. Now, what exactly does that dot product mean? Well, it represents, or we can use it rather, to determine the angle between two vectors. So if theta is the angle between two vectors u and v, where theta is between 0 and 180 degrees, then cosine of theta is equal to the dot product between u and v divided by the product of the magnitudes of vector u and vector v. So let's use the dot product to find the angle theta between our two vectors. We're also going to be using the magnitude. Vector u is -5i plus 12j. So I'm going to rewrite this in component form just because for me it's a little bit easier to work with. So u is the vector -5, 12. And vector v is 3i plus 2j, or in component form, v is the vector 3, 2. Since we want to utilize that formula above for cosine theta, let's start by looking for all of the components, starting with the dot product. U dot v is going to be equal to -5 times 3 plus 12 times 2. -5 times 3 is -15, plus 12 times 2 is 24. Our dot product is going to be 9. The magnitude of u is going to be the square root of -5 squared plus 12 squared. -5 squared is 25, plus 12 squared, which is 144, is the square root of 169. So the magnitude of u is 13. The magnitude of v is going to be the square root of 3 squared plus 2 squared. 9 plus 4, this is the square root of 13, is the magnitude of v. Putting this all together, we know that cosine of theta is equal to that dot product, 9, divided by the product of those magnitudes, 13 times the square root of 13. And while we don't generally like to leave radicals in the denominator, since we're actually going to be using inverse cosine, we don't need to simplify this. Theta is equal to inverse cosine of 9 over 13 times the square root of 13. And evaluating this, we get theta is equal to 78.93 degrees. And again, theta represents the angle between those two vectors, -5, 12 and 3, 2. Now you could sketch those two vectors to make sure that that angle theta seems reasonable. -5, 12 is going to be in the second quadrant. And I'm just sketching this. So trying to make that 12 distance look a little bit like twice that -5 distance. And then 3, 2. something like this. And looking at that angle, an angle of 78.93 degrees at least seems somewhat reasonable. It almost looks like a right angle in my picture, but an angle of about 79 degrees isn't that far off from that. And I did just sketch that picture. So really, we're looking for very obvious discrepancies between the angle theta that we calculate using inverse cosine and that angle that is sketched in the picture. Our next example, we're given vector u is 2, -6, and vector v is 6, 2. U dot v is equal to 2 times 6 plus -6 times 2, which is going to be 12 minus 12, or 0. The magnitude of u is the square root of 2 squared plus -6 squared. 4 plus 36 is 40, so the magnitude of u is the square root of 40. And again, I'll worry about simplifying later if necessary, but because we're plugging this into a formula, we don't really need to do a whole lot with that. Vector v, the magnitude of vector v is the square root of 6 squared plus 2 squared, which is also going to be the square root of 40. So cosine of theta is equal to 0 over the square root of 40 times the square root of 40, which is just 0 over 40, and 0 divided by 40 is 0. So what we're really looking for is, or solving for, is cosine theta is equal to 0. And we can use inverse cosine. But we know that between 0 and 180 degrees, cosine of theta is equal to 0 when theta is equal to 90 degrees. Now, this is a pretty special case here. And we're going to come back to it here after we go through this table. So the dot product, the value of our dot product can actually tell us something about that angle between our vectors. If the dot product is positive, then that tells me that the angle is going to be acute, or between 0 and 90 degrees. If the dot product is 0, which we've seen this twice now, we saw this in an example up here where you got a dot product of 0, and in this most recent example, we found a dot product of 0. If the dot product is 0, then the angle between the two is a right angle, or 90 degrees. Now, there's a special name when we have a dot product of 0. This is called orthogonal vectors. And that was what we observed in that last example. Those two vectors, 2, -6, and 6, 2, those were orthogonal vectors. If the dot product happens to be negative, then our angle between vectors is obtuse, or between 90 and 180 degrees.